Yeah, welcome to one more videos on memories. So let us just have a recap of the working of SRAM. So SRAM, which stands for static random access memory. So we have seen the working of this particular RAM, which has got two back-to-back connected inverters, which will going to have a feedback loop so that the stored value will be retained forever as long as the power supply is on. So okay, let us try to recap. Okay, how do we do the read operation and how do we write it, and what are the issues involved with the dimensions of the different MOSFETs. So uh, to understand the read operation, let us try to first assume that there is a particular value that has been already stored in this particular memory location. So even though it has got two outputs, that is if you are saying it as a Q and a Q bar, the valid input, or the whenever I say okay a bit 1 is stored, so we are referring to this Q output. So this is the one what you are considering is as the valid, okay, not the valid one, the actual input that is stored here is this Q. If I say this bit holds the value of high, means this Q is equal to high, or the value is in terms of VDD, and since it is VDD, so this will be low or it will be 0 volt. So this is a value that is stored. So we know that for read operation, first and foremost thing is that both bit line and bit line bar line, both the lines are made equal to VDD, so that we call it as pre-charge. So before we actually read any particular bit on a memory, the bit lines are pre-charged to VDD. So VDD is the value that is stored onto that has been applied to both bit line and bit line bar, and then we apply, and then we make this okay word line equal to high. Whenever you are actually making word line equal to high, that means that you want to read the value or write the value. So this is a word line. I want to, since I'm doing a read operation, I want to actually read the value that is stored in this particular bit. So since we know that BL and BL bar have been made high, now upon making this word line equal to high, after some time, whatever is the bit line value that is retained, if the bit line value retained is equal to VDD, then I'll say the bit that is stored in this particular SRAM is the logic high. If the bit line becomes equal to 0 volt, then I'll say the stored value is equal to low. Stored value is a low value is stored in this particular memory location. So since we have assumed the value of this particular bit to be stored as high, as soon as I make bit line as well as okay, bit line bar as high and make this word line as 1, we have seen that. So for a proper operation, the dimension of M1 should be larger compared to the dimension of M5. So M5 should have a lower dimension, meaning that the resistance offered by R1 should be less than the resistance offered by R5, or in the sense whatever value of high that is there here should not alter this position, the voltage at this point, which is equal to 0 volt. It should not go above the threshold voltage of this transistor during the read operation. If something like that happens, we say it as writing a value of 1 onto the Q bar, or we also say it as read upset. So in order to avoid this read upset, this is read upset, so we have defined a term called as cell ratio, which is defined as the W by L ratio of first transistor to W by L ratio of the pass transistor, which is 5. This should be always greater than 1.2. This number 1.2 came, of course it is there specified in the textbook, that if the value of CR is less more than 1.2, so there is no problem of this voltage going below, sorry, going above, this will never go, uh, the value will not go above 0.4. Suppose the value of CR is less than 1.2, So this is how it was happening. So this was 1.2 and this is actually CR, this is the voltage. Now you can see this is 0.4, this is maybe 0.6, so this is 0.8 and this is 1 volt, and this is 1.8 and this is as in that 1.6, this is 1, this is maybe zero point 0.8. So what I mean to say is, if the CR value is more than 1.2, that is if it is there in this region, if it is there in this region, we know that the value the voltage at this X point, the voltage at this point is always less than 0.4, so that this transistor will not turn on, so that it remains in the previous state of H. So you'll be actually properly reading the value if you are maintaining the resistance offered by this high compared to the resistance offered by this. So in order to make this CR value larger, so we know that W by L of 1 and W by L of 5 is there, so this should be far greater than 1, meaning W by L of 1 should be far greater than W by L of 5. There are different ways of achieving this. So one of the way of achieving this is, I can make, okay, one of the possibilities, how do I make this this condition to satisfy? You make L5 as large. If I make the length of the fifth transistor large, the resistance R5 will increase. If the resistance R5 increases, then you can certainly satisfy this condition far greater than 1. But if the length of this transistor M5 has increased, so this will actually increase the capacitance offered by this M5, which is connected to this BL bar line, which will actually load the bit line. So because of loading effect, the idea of increasing the L5 to increase increase in the value of L5 will actually reduce the value of this W by L of 5, which will certainly increase the CR, So instead of increasing the value of L5, which will certainly load your bit line, so you don't do this option. You look at the second possible option. Second possible option to have a larger value of CR is increase the dimension of your first transistor. If I increase the dimension of first transistor, naturally CR will certainly increase. Because if you increase the dimension of this W1, you can see it is proportional to CR. If I increase W1, CR also increases. Of course, when you increase this W1, CR increases. Of course, please retain the dimension of this M5 transistor as small as possible, so that it doesn't load the previous circuit. So as W1 is increased, the resistance offered by R1 reduces, so that you can able to achieve this CR value larger. So this way we have to carefully size the dimension of the transistor, so that M1 offers lesser resistance compared to M5. That will ensure that you are doing a proper read operation. Next, let us see, okay, how do we write the value onto this particular bit. So since we have assumed the value of high is already stored in this, let us try to write a logic low, that is 0 volt onto this particular SRAM. If at all, if you want to write 0 onto this, so we have to the first condition is that whatever you want to write, so that should be the value of bit line. So bit line should be equal to 0 volt, and bit line bar should be, of course, it should be VDD. It should be equal to VDD. So that means this should be low and this should be high. So whenever this is low and this is high, you can see now you are doing the write operation. During write operation, BL and BL bars are complement. During the read operation, both are pre-charged and the process will start. So since you are doing the write operation, this is low, this is high. Now once you make this low and high, you make this word line equal to 1. Since we have made the dimension of this particular transistor low enough, so that it has got high resistance. This high will not make this the existing low value cannot become high, because this cannot drive this, because you have a, or it takes longer time for this to go to high, because this is having high resistance, and this won't go high because this is always on. It is actually pulling it down to 0. Let us see from the other side. If this is low, and if it is already high is there, now we can see as soon as you make this word line equal to 1, this transistor turns on. This was also on earlier. Whenever both the transistors are on, the voltage at this point, which is high, can remain as high due to this transistor, can go to low because of this transistor. Now the value at this point can remain as high or can go as low, depending on which one is stronger, whether M4 is stronger or M6 is stronger. So what we are supposed to have is, this voltage H, whatever you have, has to be overwritten by the actual value what you want to write it, because you are doing a write operation. Now this low should reach over here. So what do you mean by low should reach over here? Whatever the high value that is stored earlier has to discharge. Now for this to discharge, the resistance offered by M6 should be less, and this M4, which is already on because of your previous state, should have higher resistance, so that this discharge should be faster and charging should be slower. So in order to achieve that, we call something what is called as pull-up ratio. So this is pull-up ratio is nothing but W by L of 4 by W by L of 6. So we should have this W by L of 4 by W by L of should be as small as possible. If it is as small as possible, then there is a possibility that this can of course this can go to a voltage which is certainly lower than the threshold voltage. Because what will happen is, suppose if you say this is PR and this is the voltage at, okay, let me say it as Y, so this, let us call it as V of Y. Suppose if you draw a line, so this is again for a particular dimension of the transistor. So if it is 1.8, see, now this will be 0.4, this is 0.3, this is 0.5. So what should happen now is, so the transistor, whatever high you have, should be actually gone to, so because this should discharge. If this discharges, then this becomes low. When this becomes low, this turns up and this will going to turn on. Basically what we want to have is, the PR value should be far less than, in this particular case 1.8. So what is the meaning of this far less than 1.8 is, so this actually far less than 1.8 will make sure that the voltage that is there at this Vy, the node Y, should go below 0.4, so that this transistor turns off. When this is off, so when the, of course when this is off, then this also starts charging. More than that, whenever this totally discharges, you're going to have a voltage as low. When this is low, this transistor or this inverter will be this NMOS will turn off, this will turn on. Whenever this turns on, the voltage here rises. When this is high, what will happen to this? The high will come over here and this will be low. So this, of course, whenever this turns on, the voltage whatever that was stored here will also go to 0. So you'll be actually writing a low onto this line. So making this particular point low will happen only when the W by L of 6 should be far greater than W by L of 4, which will ensure that resistance R6 is far less than resistance R4, so that value that is stored H will become low, as soon as you make your word line equal to 1. Okay, now you can see uh, we have what is the number of transistors required to realize 1 bit of RAM. You can see this is 2 for one inverter, another 2 for one more inverter, and 2 pass transistors required. So you totally require 6 transistor SRAM. So this is also called as 6T SRAM because it requires 6 transistor to realize 1 bit of static RAM. So since the number of bits that are stored, bits that are available in a memory is very high in terms of millions and billions, so there is no point in having 6 transistors for a single bit. The improvised version of this SRAM, instead of having all 6 transistors, we can replace the pull-up transistor, which are NMOS, by simply resistors. Now we can see what I have is something like this now. So now this will, the advantage of this is VDD, and this is similar to that. This is your word line. Okay, this you can ground it, and this is your bit line bar, and this is your bit line. So this is RD, this is also RD. You keep the resistances very high. If you keep the resistances very high, so the advantage of this particular again, this is also SRAM. This is also SRAM. So under normal condition, assume that if high is stored in this, so this high will going to make this transistor on, then this is on, means so this will be low. This low will going to turn this off, and this is off. Okay, the value that is stored here is high, so this will going to retain the value. That's why it is called as static. And during the read and write operation, the resistance of this is made very less compared to this, because RD is usually high, so you make the dimension of this slightly large so that the writing can easily happen. And for making the reading operation proper, make sure that this dimension of this M1 transistor should be sufficiently high, so that resistance offered by this is less compared to this M5 transistor. M5 transistor should be of a bit lower dimension, so that it offers high resistance as well as it is not contributing too much to your bit line bar capacitance. Because the dimension is less, then the capacitance that is added to this bit line bar is also less. So this way we can able to have an improvised SRAM with only 4 transistors. Usually these RDs will be of a larger value. So this is of larger in terms of resistance. So which can be realized using very thin layout positions. You can able to realize a very large resistance of RD. So this way we can able to certainly reduce the number of transistor per single bit representation in SRAM. Instead of 6, you can go with only 4 transistors. So in the next class or in the next video, we'll see how do we do the DRAM, that is the dynamic random access memory. So let us again read the process of how do I read the value that is stored in DRAM, how do I write it, and all those stuff.